Woohoo! Welcome back. Tonight we're going to be talking about one-to-one functions and their inverses. Yay! And we're going to start off with a very basic question. The question that started us off in Chapter 2, which is, what is a function? And let me remind you that a function says if you have a question, that should correspond to one answer. Oops. So in other words, if you have a point in the domain and it corresponds to a point in the range, that's awesome. If you have a point in the domain and it corresponds with 2 points in the range, that's not awesome. So we got awesome and not awesome. So, is f of x equal x squared a function? Well, let's just go ahead and take a look. Let's draw some Venn diagrams. Y equals x squared. Start with some points. If x is 0, that corresponds with what y value? 0, because 0 squared is 0. Nice. I'm going to pick the point 2. That corresponds with 4. Great, because 2 squared is 4. And then I'm going to pick the point -2. And I'm going to say, well, -2 also corresponds with 4. This is f of x right here, our correspondence. And, but that's okay. It is okay if 2 different elements of the domain correspond with the same element of the range. So it's okay if you have matching answers. So this is yes, it is a function. Woohoo! Happy, happy, joy, joy. So the next question is an interesting one. It says, what if we swap x and y? What if we turn it around? So the first thing I want to convince you of is that basically this would be asking us to take the arrows and put them in a different direction. So if I took these arrows and I pointed them the other way, and that's an interesting question. What would that look like? Well, here, the first thing that you're going to notice is that I'm going to have x equals y squared, and I'm going to have y. And that should make you a little bit uncomfortable to have the formula over here, right? Usually we've got the independent variable, and then the formula tells us what the dependent variable is. So this is already a little wonky. But if we're swapping x and y, then I've got the points 0 and 4 over here. And then I've got the points 0 and 2 and -2, right? Because we've swapped x and y. And so y squared, so x equals y squared. So if y is 0, x corresponds with, right? So 0 equals 0 squared. And 4 equals 2 squared. So that's good. I got an arrow there. And then 4 also equals -2 squared. And there's a problem. I've got a problem where I've got a single point over here is going to 2 answers. This is a situation where a question corresponds to 2 answers, and that's not a function. And remember, the whole point we're setting up functions is just to make it easier to work with. If you don't know what the answer is, if you don't know exactly what element you're corresponding to in the range, then it's going to be really hard to do the other work we're going to be doing. So we intentionally set this up. We said you can't have more than one answer. And so x squared is a function going this way, but if we try to turn it around, no dice. And so now the question becomes, how would you create a function that would also be a function if you swap x and y. So in other words, we want something that's a function when you go left to right, and we want it to still be a function if we go right to left. Okay, so let's take a look. So the first way we want to talk about it is we want to say, I'm going to just tell you, this is something called a one-to-one function. And just like with everything else in math, I'm going to try to convince you that the phrase one-to-one is very precise and very clear. It is intended to be exactly what it is. So if you can imagine, what does one-to-one? One element in the domain corresponds to one element in the range, or one x corresponds to one y. So what does that look like? So if here's your x and here's your y, then each element over here, and I mean, you can make it as fancy as you want, but basically each element over here corresponds to exactly one element. And can they cross? Absolutely, crossing is fine, as long as each one here only matches one over there, and each one over here only matches one. So in other words, there's no x. So nothing, there's none of this and none of this. So nobody shares. This is one-to-one. No double answers. And no matching answers. And I think one-to-one is actually pretty good with describing that situation. So this is a special category of functions. Now, is x squared still a function? Absolutely. This is a perfectly good function. This is a function. Yes, absolutely. This is a function. However, it is not one-to-one. This is a one-to-one function. So what does that mean? Well, you know, at some point we're going to have to bring some algebra into it. So let's go through what the algebra is. A lot of times it's actually hard to describe what something is, and it's much easier to describe what it isn't, which is kind of an interesting fact about math. So the way we describe one-to-one is we talk about what it isn't. In order to be one-to-one, a function must satisfy the following. If f of x1 is not equal to f of x2, then x1 cannot be equal to x2. And if x1 does not equal x2, then f of x1 cannot be x2. F of x2. So what does that mean? So in other words, if x1 is not equal to x2, oops, that was funny. Oh, that's not going to cooperate with me, is it? There. Nope. Oh my goodness, this is a great opportunity for me to show, oh look, it's a pterodactyl. Ah, pterodactyl. Ooh, the sound of a brand new, a brand new whiteout guy. Oh, so smooth, so nice. If x1 is not equal to x2, then y1 cannot be equal to y2. And if y1 is not equal to y2, then x1 is not equal to x2. So in other words, if the x's don't match, the y's can't match. If the y's don't match, the x's can't match. and vice versa. Okay? So, no x corresponds with more than one y, no y's correspond with more than one x. In other words, it's 1, 2, 1. Okay, woohoo! So, how do we know if something is 1 to 1? Well, a regular function follows something called the vertical line test. And you'll remember that the vertical line test, for example, if I have a parabola, the vertical line test says each vertical line only passes through one point. Ooh, let me write in my x and y. So let's take a look. What happens if I look at this parabola that I've drawn? Does it pass the horizontal line test? And the answer is, ooh, no. What happens right there? Right there, I have two x's correspond to the same y, right? Do you see that? This point right here and this point right here both correspond with that y. So a regular function has to find the vertical line test. The horizontal line test is another step above. So this is not 1 to 1. So now the question becomes, what would a function have to look like to be 1 to 1? So let's think about this. The parabola failed because it scooped down and then it scooped up again, and a horizontal line crosses through 2 points. So if you want a 1 to 1 function, wherever you're starting, we could start the parabola, but then you can't scoop back up. So no matter where you go, you have to keep going in that same direction. So for example, if this is g of x, this passes the horizontal line test and the vertical line test. Remember, the vertical line test is that it's a function. And take a look, think about it, think about vertical lines going through. And I claim that any vertical line goes through only one point, so it's a function. And then the horizontal line test if it passes that, which you want to think about horizontal lines, and I claim every horizontal line goes through exactly 1 point. So that tells us it's 1, 2, 1. So this is a function which is also 1 to 1. Okay, let's think about another one. Could you be a function that's increasing? I claim so. I claim, and I'm not going to say it's a boring line, but I'm going to say I could pick an increasing line like that. That passes both the vertical line test, right? Vertical lines, and the horizontal line test. This is a 1 to 1 function. So here are a couple questions for you. could you change direction and still be a one-to-one function? So could you be heading down or heading up and decide, like if you're heading down, decide to head back up? I claim no, because then you would fail the horizontal line test. If you were heading up and then changed direction and came back down, again, you would fail the horizontal line test. So one-to-one functions only increase or decrease. Could you be a horizontal, oh, you can't see that. Could you be a horizontal line? And I claim no, because then you would fail the horizontal line test. All the points would be on that line. That would not work, right? Could you be a vertical line? Nope, because then you're not a function. So you have to be a function which starts going in one direction and keeps going, either decreasing or increasing. Okay, so then the last thing we'll want to do before we move on is we have to be able to prove that a function is one-to-one. Now, these are not easy. Proving a function is not one-to-one is actually pretty easy. Proving that a function is not one-to-one requires that all you need to do is find that point like this. So when x equals 4, that corresponds to y equals 2 and y equals -2, right? That was the problem we had a situation where 2 and -2 both correspond to y equals 4. But when we've swapped it around, we end up with a problem, right? So if all we have to do is find a pair of points that correspond to the same y, we're done. We're like not one-to-one. What if we want to prove it is one-to-one? So if we believe it is one-to-one, then we're not going to be able to find a counterexample because we think it is one-to-one. So what we could do is we could go through all of the infinite number of points and prove they all work, which is going to take a long time. It's really going to take a long time. Or we can start with an assumption that it isn't one-to-one. So assume f of x is not one-to-one. This means that there exist x1 and x2 such that f of x1 equals f of x2. Now, we know what f of x is. So we're saying, okay, I've got two x values that give us the same y value. So over here, f of x1 has got to be x1 minus 3. Over here, f of x2 is x2 minus 3. So in other words, we're saying these two values are equal, but these two values are different. Okay, so then what? Well, if I add 3 to both sides, so in other words, if the y's are equal, then the x's are equal. That's it. It's one-to-one. So this is a counter example. So if we assume it's not one-to-one, then we need to be able to find two values of x which give us the same value of y, which means x1 minus 3 and x2 minus 3 must be equal. But if those two are equal, then the x's are equal. So if the y's are equal, then the x's are equal. So this is one-to-one. Now, this is a very simple example of one very famous type of proof that we use in math, and you're going to see it again. For us, we're just going to use it in this one little setup, and usually the situation will not be that complicated. You can only use this proof easily when you believe something is one-to-one. If you believe it is not one-to-one, you just need to find a counterexample like we did in the first problem. Okay, so we're going to leave it there. I want to thank the pterodactyl for distracting everyone. Woohoo. And thank my tree friend because we're doing composition. So, of course, decomposition as well. And we're going to talk next about what we're going to do with one-to-one functions. It's going to be very exciting. So come back. But this was a long enough video, so take a break. Get something nice to eat, get a snack, get something to drink, maybe take a nap, go to bed, watch some TV, whatever it is you do to relax your brain a little bit. Maybe, look at something green, go running, read a book, whatever it is that you do to relax, and then come back and watch the second video, and we'll do cool and exciting things. Woohoo! Math on, you guys are awesome. Woohoo.